So we're going to discuss from the equation 4.149 in your book, all the way to the equation 4.152. So what is the discussion here? This is in the page, just for you to know, in the page 169 of the book, Griffiths, third edition. And what is the discussion here is, we already know the eigenvectors and the eigenvalues for the SZ operator. Now, what we want to do is to find the eigenvalues and the eigenvectors for the Sx. Okay, so this is going to be the first step. And then, if we are given a certain general state, like this, written using the basis of Sz, how can we rewrite this state, but now using the basis of X? Okay, so that's the story. All right, so let's start from the beginning. So, in terms of the spin operator in the Z direction, what we know about it? We have two eigenvectors. The eigenvector chi plus, I'm going to put it Z because I'm talking about the Z, chi plus, which is this vector 1, 0. If you want, there are other ways to denote that same state. You could say, oh, this is the spin pointing up in the Z direction. Another way is, oh, this is the spin where S is half and M is plus half. So these are all the same, different ways to say the same thing. The other eigenvector, the other eigenstate for SZ is what we are denoting chi minus. And this is the vector 0, 1. Again, we can talk about a spin pointing down in the Z direction. We can talk about S being half and M being minus half. Okay, so these are all possible notations. The two vectors are orthogonal. They are also normalized, so they are orthonormal. For the one that is pointing up, the eigenvalue is plus h bar over 2. And for the one pointing down is minus h bar over 2. So this we already know. So what we want to do now is to find the eigenvectors and the eigenvalues for Sx. So what is this operator Sx? It's a matrix written like this, h bar over 2, and here comes the Pauli matrix sigma x, which has off-diagonal elements. Okay, so to find the eigenvalues and the eigenstates, what do we have to do? Well, we are going to pick this matrix. So let's write this matrix. And in the diagonal, I'm going to subtract by a certain letter, which is going to be an indication for our eigenvalues. I'll call it lambda. So 0 minus lambda is minus lambda. And the other element here, 0 minus lambda is lambda. Okay. And what we are going to do now, we are going to compute the determinant. That's the way to get eigenvalues, right? To get the equation of eigenvalues. This determinant has to be 0. We already talked about this since chapter 3. So that's the equation that we are going to solve. What is this equation? Well, the diagonal, lambda squared, minus the off diagonal, minus h bar squared over 4, has to be 0. So this is what we have to solve to find the eigenvalues. There are two possibilities. We have the eigenvalue plus h bar over 2, and we have the eigenvalue minus h bar over 2. Just as the sigma, the SZ, we get again the same eigenvalues, the same two possibilities. Very good. Now what we want to know is, what is the eigenstate associated with this one? And what is the eigenstate associated with that one? So let's start with the plus. Well, what does eigenstate, eigenvector mean? That means we are going to apply this Sx on this vector that we don't know yet. We'll be calling it the chi plus, but now in the x direction, what is this going to give us? Plus h bar over 2 and the vector again. That's why it is an eigenvector. Okay, so what is this vector chi plus in the x direction? Well, so we will have to solve this equation. That's x we know, we already wrote, so it's 0, h bar over 2, h bar over 2, and 0. That vector we don't know, we are trying to find it, so I'm going to call it, give two letters for it, for example, alpha and beta, equals to h bar over 2, alpha and beta. With that, we should be able to find this vector, because now we have two equations. So what are the two equations? Well, if we go with the top line, what we are going to get is that h bar over 2 multiplied, h bar over 2 multiplied by beta should give us h bar over 2 multiplied by alpha. Okay, and now if we look at the bottom line, it's going to be h bar over 2 multiplied by alpha equals to, since that is the second line, it will give us this second element, which is then h bar over 2 multiplied by beta. Well, things didn't help us much, well, in the sense that at the end we have just one equation, and the two of them are equal. And what we conclude from these two equations is just that alpha is equal to beta. Okay, so that means that vector that we are trying to find is equal to alpha alpha. Both elements are equal. How can we find what this alpha is? Now we are going to resort to normalization. Now the vector has to be normalized, so I'm going to write it like this. This has to be equal to 1. Now the bra and the cat. So that means for the bra, alpha conjugate, the cat is the column alpha alpha. And if we do this product, we are going to get alpha, absolute value of alpha squared twice, because both terms give us the same, and this has to be 1 for normalization. Very good. So then we found that this alpha is 1 over square root of 2. And so our state, the state that we were after, is this. Okay. So this is the eigenvector associated with the eigenvalue h bar over 2. So this is the eigenvector chi plus in the x direction. All right, so now let's go for the other one. And for the other one, we want to obtain the vector associated with this eigenvalue minus, not the negative one. So again, the same story. We are going to go Sx acting on this vector that we don't know yet, the minus. So this vector here gives us minus h bar over 2. And so the procedure is going to be very similar to what we did before, right? The matrix is 0, h bar over 2, h bar over 2, 0. I don't know what the vector is. I'm going to call it alpha and beta. Minus h bar over 2, alpha and beta. And you're going to see, again, we get two equations, and it's going to be h bar over 2 beta from this first line, gives us this top element, minus h bar over 2 alpha. From the second line, h bar over 2 alpha, right? H bar over 2 alpha gives us minus h bar over 2 beta. So again, the two equations are equal, but what we conclude is that alpha is equal to minus beta. So that vector is alpha and minus alpha. And how are we going to get alpha? Normalization. This has to be 1. So alpha and minus alpha conjugate multiplied by alpha and minus alpha will give us, again, 2 absolute value square of alpha equal to 1. So alpha is 1 over square root of 2. So our other vector is chi minus, in the x direction, is 1 over square root of 2, 1 and minus 1. Okay, so this is the other eigenvector of Sx, which is the one associated with the eigenvalue minus h bar over 2. So we found both eigenvectors and their corresponding eigenvalues. So let's just summarize things here. For this operator, Sx, we have two eigenvectors. The chi plus is 1 over square root of 2, 1, 1, and it has eigenvalue plus h bar over 2. And we have the other eigenvector chi minus in the x direction, 1 over square root of 2, 1 and minus 1. And this is the one that has eigenvalue minus h bar over 2. Very good. Now, suppose we were given a certain general state. Okay? So suppose we are given a state that we are calling it chi, and this state is A, B. Okay. Well, this is a state written using the basis of the SZ. So this means A1, 0 plus B0, 1. Okay, so this A square is the probability that if I measure SZ, I'm going to get the eigenvalue plus h bar over 2. Okay, so this is the probability that I'll get that. And b squared is the probability that if we measure the SZ, we are going to get minus h bar over 2. Okay? From normalization, we know the absolute value square of A plus the absolute value square of B has to be 1. Okay, now, how can we write the same state that we have here? But instead of using these eigenvectors of SZ, how can we write this state using the eigenvectors of Sx? Okay, so how can we do that? Well, we have to find what is this component A for the chi in the x direction, and what is this component B for the chi in the x direction. Okay, so how do we do that? Well, one method is brute force. What do I mean by brute force? Just write down what that chi is. And from here, we are going to have two equations, and from them we can find what big A is and what big B is, right? So what are these two equations? We have that A plus B, the top line. So what I'm doing is I'm picking this A plus B equal to little a. So this is one equation. The other equation is the bottom. So it's A minus B over square root of 2, giving us little b. Okay? So from here, we can find the big A and the big B. Okay? So if we sum these two equations, we find that 2 big A square root of 2 is A plus B. So that means that big A is A plus B square root of 2. And if we do the same thing for B, now but subtracting the two equations, we are going to find that big B is A minus B over square root of 2. Okay, so solving those two equations, that's what we get. Big A and big B. So if we are given this state here. And the question now is, what is the probability that when we measure Sx, okay, when we measure Sx, what is the probability that we are going to get the state chi plus, that we are going to collapse the spin into this state of chi plus? That is, what is the probability that we are going to measure plus h bar over 2 for Sx, okay? And what is the probability then? The probability, so let's put here the probability that we get plus h bar over 2 when we measure Sx is absolute value square of big A. What is that? Absolute value square of A plus B divided by 2. And what is the probability that when we do the same measurement, we get minus h bar over 2? Well, is that B squared, which is A minus B absolute value square over 2. Okay, very good. This is one way, okay, to get this this coefficient A and B. This is one way, brute force, as I said, putting the vectors, writing down the vectors and trying to find these equations to get big A and big B. The other method is, let's come down here. The other method is what we are familiar with since chapter 2. We have here a vector, and we are trying to find what are these coefficients, this A and this B. Okay. Why do I say that we know this since chapter 2? Because in chapter 2, we used to do the same thing. We had a certain initial state, and we would write it in terms of the eigenstates, the solutions that we would get from the Hamiltonian, right? So we had to find these coefficients. And how would we find these coefficients? This coefficient was this integral, where we would put this psi in front here, the conjugate, and then we would put this initial state there and solve the integral, right? Which in chapter 3 we said another notation for that is the bra and the cat, right? Well, what we are trying to do now is the same thing. We are trying to find A and B. So how we can find A? Well, just following what we wrote here, we are going to say that A is equal to the vector that is given. So this vector that is given, and this one in the bra. And we are going to get A. So this is a faster way than trying to solve these equations. Here we just have to play with this product. So what is this? The chi plus in the x direction is 1 over square root of 2, 1 and 1. And what is the chi? A and B. So you see that in one shot, we just get that the big A is A plus B square root of 2, as we had found here. Yeah. And the same thing for B. How are we going to find B? B is the same story. The cat is the vector that is given, and then for the bra, we put the chi minus. And we are going to get, we put it here, what we had before, of course, 1 over square root of 2, 1 minus 1 is chi minus. and the vector AB. So then that big B is A minus B square root of 2. Okay, so that's the end of the story, right? So our initial or the state chi that was given to us, the general state chi that was given to us can now be written in terms of chi plus and chi minus for the Sx. It's going to be A plus B over square root of 2 of chi plus x and A minus B over square root of 2 of chi minus x. Okay, and with that, we can find the expectation value of Sx. We can find the probabilities of finding it in the chi plus or finding it in the chi minus. So there is a good example. There is also a video for it, which is the example 4.2. And there are some good problems as well, just repeating this same idea, the same kind of problems again.